Hi, I'm Manav, and I'm presenting today along with Shanaka and Suresh. Our project is developing a satellite image classifier using neural networks. Here's a brief overview of problem, the approach, and the tools that we used. So deforestation is a major issue around the world, but especially so in the Amazon rainforest. Every minute we lose an area of forest equivalent to about 48 football fields, and this causes habitat loss, climate change, displaces native populations. So better data about the location of deforestation can really help governments or local organizations respond more quickly and effectively. We found a challenge put on by Planet Labs and Kaggle.com. The task is to classify and label satellite images that they've taken to identify deforestation and other features like logging, mining, and burning of trees. Kaggle is a data science platform that lets entities put on competitions, essentially crowdsourcing them. So they give us training data, but they also have a test set that they use that's used for scoring. Planet Labs is actually the largest holder of private satellites. They have imagery that's taken on a daily basis up to 3-meter resolution in the U.S. They plan to expand that around the world. For our project, we also utilized Google Cloud. That enables us to use GPU-accelerated instances, which really helped us train our models a lot faster. I'll include some setup information in the description below, along with our project. So about GPU acceleration. NVIDIA, CUDA, and CDU-NN libraries enable a massive amount of acceleration for tasks that are parallel. So we've seen speedups as much as 50 times over just using a CPU. CUDA and CUDNN are compatible with neural networks and TensorFlow. So we used Keras and TensorFlow for this project. TensorFlow is Google's machine learning platform, and Keras, which is also developed by someone at Google, is kind of a wraparound TensorFlow. It's compatible with other frameworks, but it makes the code just a lot more readable. It's easy to use, and it helps us iterate faster as a result. Keras also has a lot of built-in optimizations for various activation functions and optimizers. So I'm not going to go into too much background on neural networks, but today's computational power has basically made a lot of tasks that were almost impossible a few years ago a lot more feasible now. So our problem is actually one of supervised learning. We're given image tags for all of the data that we have. So there's actually a lot of methods for image classification. There's decision trees, gradient boosting, random forests. But we're going to concentrate on neural networks because they've shown the greatest accuracy in a lot of the public data sets. One additional hurdle that we had was that we're facing a multi-label, multi-class problem. What this means that for any given image, we can have multiple labels. Like this example over here, you can see that if it's multi-label, we can label it as both seas and trees. We also utilize something called the F-beta score in the evaluation of our model and for this competition scoring. The F-beta is actually derived from the F-score that you see over here. But in essence, what it does is it gives us a better evaluation of the model's accuracy by helping us avoid false positives and false negatives. Keras has a lot of built-in optimizers. We found that most of them were kind of like some variation of the other, but in general, we found Atom to give us the best performance while letting us also run fewer epochs. The most basic neural network is the multi-layer perceptron, also just called an artificial neural network. It's fully connected in each layer, but not in between. So we actually tried a model using something like this, and we got a 90% validation accuracy and an F-score of around 0.75, which is not too bad. So I'll also briefly go over convolutional neural networks. They use layers and filters to extract features by looking for patterns in images. So here's an animated explanation of that here. And pooling is something that's used to reduce the size and prevent overfitting of models. Lastly, dropout is something that we used extensively as well, and just like pooling, it helps reduce overfitting. I'll now pass it on to Suresh.
Thanks, Mano. Good evening, everyone. So let me give a brief introduction about myself. My name is Suresh. This is my first semester with Harvard Extension School. I enrolled in all four courses required for a graduate certificate in data science. Today I'm going to go over on like how to get the data from Kaggle and then also on the data exploration part. That's basically preliminary analysis on the data. So what we get from the Kaggle. So let me show you. Let's go. So once you go into the Kaggle, you can see the different competitions. If you don't have an account, it's pretty simple. You can register it and then go to the Planet Understanding Amazon space. So this is the competition that we are interested in. And you see the data tab here. So just click on the data tab and you'll see there are like 11 files related to this competition. So you just need to download this into your machine or like a cloud, wherever you're going to run it. Okay. So once that is done, so obviously you got the like tar files, you just need to untar them. And I just wrote a simple script so to find out the size and and also how many files are there in each file. If you observe, like we have a training data set and also test data set, and you have two different types of training data, so JPEGs and TIFF. The reason for it is the TIFF is basically high resolution files, and you see it takes like 30 times more space than JPEGs. It's the same number of files, so 40,000 files in training set for JPEG and also for TIFF. And also test you have a 40,000 files. And train.csv is basically classification file where you have a image name and tags, right? If you observe, for each training image, sometimes the multiple tags are attached to it. That means the agriculture is one of the classification of this image, and also it's a clear. This means agriculture, and also weather is clear, and there's some water flowing around. Maybe a river is there, right? So there are multiple tags are attached to each image. That's what we observed, and basically I'm just trying to I'm just breaking down these tags so that I can do more analysis on this. And if you see this bar chart, so I'm trying to find out like which classification is appeared many number of times in like each image, right? If you see the top five, it's a primary, like it appears like 37,000 times out of 40,000. Pretty much most of them are primary. Primary is basically it is a dense tree area, and the satellite images are for Amazon space. It makes sense. It's a forest, so most of them are primary. And you can see clear, that is the weather is clear, and agriculture land, road and water. So and there are like other classifications, but they did not appear many times. Let's move on to the next slide. Here, basically, I did a matrix of co-occurrence. What I meant is, for example, let's take an agriculture and sea water. They together appear, or they together tag to the 2,700 images. This matrix will tell you like how each classification co-occur with the other one. And this is just a heat map, so it's just a representation of the previous matrix in visual form. That's it. So diagonal is pretty much it's the same primary versus primary. You can ignore the diagonal and you can observe the other one. You can see this clear and primary appears maybe 30,000 plus times. So it's a it's a better way to visualize, right? So instead of going to matrix, it's easy to visualize. I'm interested in looking into the weather labels because generally they should not overlap. That's what I'm trying to find out, and I run the query for that, and then see it makes sense. They didn't overlap, so it's only in the diagonal, and it makes sense. Clear, party, cloudy, haze, cloudy. So they're mutually exclusive, right? So that's what I'm trying to find out. So do they have anything overlap? So they didn't. That's good. And this is just a heat map for the same table. And I try to get for more information on some few labels: agriculture, water, road, and background, and they appear to be overlapped. So it makes sense because agriculture and you can say water and agriculture, they go like 2000 times, and then water and say road, you can see 2000 times they appeared. Okay, um, let's go to the just want to see the actual images. Right now we just see the classification file. So I just pulled like a 9 sample images and see like how they tagged it in. If you see, all of them are tagged as a primary, because most of them are like a forest, right? You see the density area. And let's look into this image. So yeah, it appears to be there's a road, right? That's why it tagged as a road too. And this one you see the river is flowing, and that's why it's tagged as a water. And now I will hand it over to my other project mate. Thank you very much.
This is Shanaka. Thanks, Manav and Suresh. We started our model building with 2 convolutional layers and we achieved 63% accuracy, which was not that satisfactory. So we decided we need to go deeper. Transfer learning is one of the techniques used in machine learning, just solving one problem and applying the knowledge to a different but related problem. There's usually insufficient data to train a model from scratch, and it takes a lot of computational power to do so. It could take weeks to train a modern CNN across GPUs. Following some of the popular models used recently, like VGG16, Google Net Inception, V3, V4. So for our solution, we'll be using VGG16 model and we'll be fine-tuning it. This is named after the Visual Geometry Group from Oxford, and it used to win the ImageNet competition back in 2014. It has 5 layers of convolutional blocks and 1 fully connected layer. So this is the overview of the proposed model. We have 5 blocks of convolutional layers, which is coming from VGG16, and on top we have our fully connected layer. This is the strategy we will be using. We are going to initiate the VGG16 model with ImageNet weights, and then we're going to extract and save bottleneck features out from VGG16. We're going to load our saved data and train a fully connected model on top of that, and we're going to call it top model. We're going to create the full model combining the VGG16 with the top model. Then we'll be initiating the convolutional base of VGG16 and load its weights. We're going to load the top model weight saved in step 3, and we're going to freeze the layers up to convolutional block 4. Finally, we start training the full model with a very slow learning rate. Alright, let's dive into the code. We'll be using TensorFlow and Keras for our solution, and we are setting up the Conda environment, and we'll be using these Python packages. So after we install Keras, we can check which backend we'll be using. So you can use TensorFlow, and you can change the configuration if you so, we'll do so. But in this case, we're not going to do anything. We're going to verify the GPU. So in my case, I have a GPU with 2 GB of RAM, and so we can prepare our data. We're going to see it as the train and test data sets into HDF5 format. So this script is going to create the H5 file, and the one below it's going to create another one for the training data set. Also, it's going to create the one-hot features. So after that, those scripts run, we can see those 2 files, and we're going to verify our labels. And so here we can see we have the one-hot encoding in our dataset. So as mentioned earlier, we started building with the 2 convolutional layers, and this is it. Then we explained about a few other models, and finally model 7, that is the best performing model. So we discussed the strategy we are going to use for building this model, and this is the TensorBoard graph for the model 7. So here we have the sequential top model and the VGG16 model down here. So we are going to import all these packages, and we are using TensorFlow backend, Here, this function is going to load the training dataset, and this one's going to load the test dataset. Some global settings. We'll be using epochs 3, batch size 3, and this is the bottleneck feature file. So first step is we're going to save the bottleneck feature, and this function is going to load the VGG16 model with image net weights, and it's going to save the bottleneck features to that file as an NumPy array. Next step is training the top model. So we'll be using the NumPy array saved earlier, and we are going to feed it into our top model. So then here we fit the model, and then we save the weights of that model down here. And here we are building the full model, combining the top model and the VGG16. So here base model we have the VGG16 and top model. Here we load the weights that we saved earlier, and here we combine those two models, base model and the top model. Here we are tracing the weights up to convolution layer 4, so those will be untrainable, and then we'll be using Adam optimizer with a very low learning rate. Here we split the datasets into test and train and validation, and we are fitting the model down here. Next we are predicting the so here you can see we are going to use the submission file and saving the prediction. So recently Kaggle added additional test dataset, so that's why we have 2 blocks here. And execution. So we set all these variables and call in the save bottleneck feature. So we can see the model summary here. We have 5 blocks of convolution layers, which is coming from VGG16. And once that script executed, it took 1837 seconds, and it saved those 2 files. Then we train in the top model. We are using 2 epochs, but ideally we should at least run 10 epochs. Since this model is very small, it's going to only take 58 seconds, which is good. And then we are going to save this weights from the fully connected model. Next, we are going to train the full model, combining the last 2. So we call the train full model method, and so here we only use epoch 1, and then next step we are going to change the test size to 0.1 and run that same method again. And so here we can see trainable parameters 9.1 million and non-trainable parameters 7.3, because we solve some of the layers. So once that is done, we can see the accuracies. It goes up to 0.96958, which is good. And then it's generating the predictions and saving to that file. So once those epochs done, we can see this weight file and model 7 submission CSC file, so we can submit it to Kaggle. And the performance of our model. So there were 2 datasets we discussed earlier. There's high resolution TIFF images with 4 channels and 64-bit, and low resolution JPEGs with 3 channels. So we used the JPEG dataset and we downsized images to this size because we only have limited time constraints and hardware constraints. But even though we use 1/10 of the data provided, we were able to secure top 14% of the Kaggle leadership board. So that's a good news, and currently we are in 30th place in the Kaggle leaderboard. And the future work will be integrating the infrared channel, and also we are planning to use the high resolution TIFF images and we are planning to use more color correction and augmentation. So performance benchmark. So to train the model, it takes about 8.25 hours. So that's why running these models are very computationally intensive and expensive. So, and this is just using 1/10 of the data available. Conclusion: we built a CNN model using VGG16 for satellite image classification. We use TensorFlow, Keras, and Python. We utilize Google Cloud. We utilize GPUs for computation, and we achieved 30th place on Kaggle leaderboard. Thanks for watching.